So my guests today are Brad Larschan. He is the CEO and co-founder of Avadain. We're going to be talking about their company, and also Kevin Wyss. He is the director of applications. Avadain is commercializing a patented technology for producing what it calls large, thin, defect-free graphene flakes. The company believes these characteristics are critical to preserving the remarkable mechanical, electrical, and thermal properties that have made graphene such a promising advanced material. We've talked a lot about this wonder material on previous podcasts, and excited to have these two gentlemen joining me on the show today. Their company has received almost a $4 million federal grant to scale up. So we're going to be talking about some exciting news with their company. And gentlemen, I'm glad to have you on the podcast today for this episode. Thanks for coming on.
Well, thanks for having us.
Thank you. Yeah,
absolutely. Absolutely. This is exciting. I had the opportunity reading about your background. We've talked about graphene, wonder material. We're going to be talking a little bit about the company, some exciting news. But before we get into the company, let's talk about you guys, if you would. We'll start with Brad, if you would share a little bit about your background, and then Kevin, if you would do the same for our audience.
Absolutely. Thanks, Jonathan. Well, my background is really as an international lawyer. It has nothing at all to do with graphene.
Awesome.
I worked for a Wall Street law firm in their Washington, D.C. office, and decided that I really wanted to do something different. I wanted to be more entrepreneurial. And I wound up in technology commercialization and partnered with the U.S.'s number one IP law firm, Fish & Richardson. And together we sought university potentially disruptive technologies from around the world, and we began commercializing them. That was back in 2010, and it was in 2016 that we wound up finding this technology, which I'll talk more about later. And this became so exciting to us that we stopped doing the technology commercialization and focused only on Avadain and LTDF Graphene.
Kevin, how about yourself?
Yeah. It's great to be on with you, Jonathan. And I'm actually a PhD scientist in materials, nanomaterials. I got my PhD at Rice University under James Tour, and who really is one of the greats in the graphene space. And so it's been great to work with Avadain. Brad and I met at a conference, and we were both on the same panel talking about graphene. And then he said, "I really want you to come work for me." And ever since then, it's been a really fun ride. Working through the scale up, working through some of the applications development. And, every step of the way, it's been really exciting to see some of the results we're getting. And it's been great.
And you guys are both in Tennessee. You're both located at opposite ends of the state almost. Kevin, you're kind of in my neck of the woods over here in the Knoxville area. And then Brad, you're in Memphis. That's where the company is based out of, correct?
Yes, we're based here in Memphis.
Okay, that's great. Great location over there. So great. Tennessee is just a great state in general for business right now.
It is. It's a great place to be right now.
So give us a little background of the company. Yeah, you've given us a little history of yourself, Brad, as an attorney. Obviously, I love the fact that you come from kind of a different background into this, so you have a unique perspective. But let's talk about kind of the startup of the company. I think I mentioned earlier at the introduction, we've talked about graphene in the past. The challenge is scaling it up to get consistency, and then also having material that's defect free, and we could talk about that. So if you would, let's start with the company and tell us a little bit about kind of the startup, the foundings, and what's going on right now.
Sure. I come from the final stage of the technology commercialization paradigm. And that is actually licensing and commercializing the technologies. So I'm not so much from the inventor side, but rather from the business side, the end use side.
Yep.
And that's important because in 2016, we were invited to the Fraunhofer Institute for Applied Solid-State Physics in Freiburg, Germany. Fraunhofer is one of the world's leading research institutions.
Mm-hmm.
And they had a very interesting thesis. They saw all of the different graphene types that were out there: graphene oxide, reduced graphene oxide, graphite platelets, nanoparticles. And they gave a presentation to me that said, look, we don't think any of these are really going to be the answer to graphene. We think that 3 physical properties are needed. You have to have a large surface area, in the microns, not in the nanometers. They has to be very, very thin atomically. Forget about 10 atomic layers. You really need to get to 5 atomic layers. And it has to be defect-free. And they proposed a research project to create a material that specifically filled what they anticipated to be the market demand. And I was intrigued and decided to invest in that in 2016. And then my co-investment partner, Panasonic, invested in 2017. And this was a moonshot because, we had 2 very bright, enthusiastic PhDs who wanted to work on this. But there was no assurance of success, Jonathan. Let me tell you. Well, sure enough, they did it.
Yeah.
Of course, it was tiny in the lab under controlled circumstances. They published a peer-reviewed paper in 2019 on it. And when they were done, we got the technology. So Panasonic and I took it over to the United States and we formed Avadain. And we formed Avadain with the intent of scaling this to mass production. That was the point.
Yep.
We were fortunate enough to receive a $3.77 million grant from NIST, the National Institute for Standards and Technology. And we used Southwest Research Institute to do the actual engineering work. And by 2024, they had really demonstrated success. By 2025, they had scaled the production 2,000 times and created what is today a full-scale reactor. So that's what really drew me to this technology, was the idea of solving a problem that industry was going to have in the future. And that is where we are today.
Yeah. So, and maybe I can direct this to you, Kevin. Talking about the technology that you're using, it's electrochemical exfoliation process. Can you give us, without giving away any proprietary secrets, give us a little bit of an overview of that and what that entails?
Yeah, absolutely. And so, and it's peer reviewed, it's out in the literature, and there's lots of patents out there. But electrochemical exfoliation is starting with graphite. And so we know that graphite we mine out of the ground, relatively abundant. It doesn't have to be those really expensive battery grades, has graphene shapes fully formed inside it. It's just stacks of it. And so we have to basically intercalate, kind of get between those sheets of paper and peel them apart very carefully. The more careful you're able to do that, the larger they remain, the thinner you're able to get them, and the fewer defects or, holes, tears, creases, things like that you're adding as you exfoliate it into a powder of these ideally very large single layer flakes. And so that's what we're doing. We're using a unique process called hydrogenation. And so typically with these, exfoliating processes, you'll see oxidation a lot. And so basically you're using a really harsh oxidizing agent to, chemically functionalize the surface of the sheet to basically pull it off. It makes it fall off once it's oxygenated. And, but that while you do that, it's a very harsh process and it's kind of irreversible. So you're adding all these holes, all these oxygen defects.
That's where you get the defects, right? That's where a lot of the defects come in during that process, or?
Exactly. Yeah. And so that gives you something called graphene oxide, which can be relatively thin, but it is not very conductive at all. It's much weaker than ideal graphene. And so people have been using that for a long time. And some companies even call that true graphene, which adds, a lot of confusion in the marketplace. But it's, a low quality. It was relatively scalable, especially 10 years ago when graphene hype was really starting to build. People said, well, this graphene oxide stuff, it's a different color. It's brown instead of black. But it's thin and it kind of looks like it. So let's just start telling everyone that we can use this instead. And so that led to some disappointment in the marketplace and in end users. But that was really kind of the first aspect of graphene. So instead of oxidation, which is the process that exfoliates it in that case, we use hydrogenation. And so we're using our electrochemical process to, instead of putting oxygen on the surface, we're putting hydrogen on the surface. And that's a much more reversible process, very easy to reverse and remove that hydrogen at the end. And so what you're left with is these very large sheets that don't have all those holes and oxygen defects present. So you end up with what you really want, a nice, large, thin, and defect-free graphene sheet, which maintains that really high strength, that incredible conductivity that we need, and is able to deliver those incredible properties to the end use.
Yeah, so consistency has been the big issue, right? I mean, you're accomplishing a number of things, creating a product at scale that is consistent, that can be used, and then you've now moved into a full-scale reactor, right? You were mentioning that earlier.
Right. And the think of it this way, Jonathan, right? There are two ways to make graphene, right?
Yeah.
One is called bottoms down. The other is called top down, bottoms up. Pardon me. Okay. So graphite is nothing more than millions of layers of graphene held together by van der Waals forces, right?
Mm-hmm.
And so the trick is to separate those layers while preserving the large natural flake size in the graphite, right? That's what we aim to do. We know the graphene is there. We just want to separate it in this reversible process that Kevin so neatly talked about, to create it. That gives you the large flakes. When you look at the bottoms up, right, that's where you take a rich hydrocarbon like methane or acetylene, something like that. You blow it up, and what's left is very, 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 very tiny particles of graphene, in the nanometer scale. And just to give you a sense for that, the large flakes that we are able to produce, which really is not us producing it. That's a misnomer. It's preserving it. We're preserving the flake that is in the graphite, right?
Yep.
That's got 200,000 times the surface area of the nanoparticles that result from blowing up a methane or acetylene. And I don't want to in any way knock this, because Kevin did his PhD thesis on the flash Joule method of creating graphene by blowing up, what was it, methane?
We did carbon black and other things like that. But yeah, it's a very similar process where you're going, it's a bottom up process where you're basically building the graphene sheets atom by atom. And so because you're building them atom by atom, they don't get very big before they stop growing. And then they start building another one, right? So you get, flakes that are, 10, 50 nanometers. Whereas,
so you're getting what larger, what is this? Because I think I was reading averaging 50 microns laterally. Is that?
Well, it's 5 microns and up laterally, but it's a 25 square microns surface area. The surface area is the key. That's really what you want to look at, is the surface area.
Surface area. Okay.
So you have the three factors of the large surface area, the thinness, the atomic thinness, and then the absence of defects. So I was just getting back to your question, Jonathan, about the manufacturability, because you've got two methods which are at exact polar opposite ends of the spectrum, right? Yeah. The bottoms up, the creation by blowing up hydrocarbon rich gases, that creates these very tiny nanoparticles that are largely, if not entirely, defect free. And then you have the separation of the natural graphene in graphite, which creates the large flakes that are essentially defect free. So those are the two ends of the spectrum. And then you have all the other graphene materials in the middle.
What about dispersion? What about that process has changed?
Yeah, I can take that question. What you're talking about that is aggregation. And so when you put too much graphene in, it starts aggregating together, and it can actually weaken your material. You're basically adding more faults to it, more errors and defects to your polyurethane, let's say, or epoxy. And so that aggregation actually hurts it and makes it worse. And that's the opposite of what graphene sells, right? And so a lot of work has been done on creating stable dispersions. And so, the graphene wants to stick back together to make graphite with those van der Waals forces. And so the use of surfactants is one pretty valuable tool we have. There's a lot of formulation work that we're doing, as well as one great part is, since we have those large flakes and they're so thin, we're able to use lower mass loadings. Okay, so if you think your audience might be familiar with graphene nanoplatelets, and so those usually have tens or hundreds of layers, right? So think about, instead of picking up one piece of paper or 3 pieces of paper, you have to pick up a whole ream, right? The mass difference there. So we're able to use, an order of magnitude less graphene. And so once you're adding less material, you don't really run into those aggregation issues as much compared to graphite nanoplatelets, which a lot of composites, because they were really cheap, especially initially, to use compared to other types of graphene. A lot of companies, including Ford Motor Company, started using graphene or graphite nanoplatelets. And so those actually kind of hit the market in 2018. Ford started using it, and it works, but you have to use a lot more of it. Think of that analogy with the ream of paper versus just a few sheets, right? The mass difference there. What you really want is, you just want one sheet to help delay your stress and distribute and bridge cracks, micro cracks, things like that, right? And if you're just adding one sheet of paper instead of a whole ream, then you're able to use a lot less mass, and then you have less aggregation as well. So our ultra low loading, because of the thinness and the lateral flake size, has really been a benefit to help us avoid that aggregation, which a lot of composite scientists, really have encountered.
Yeah. So what are some of the big opportunities right now with this material that you're seeing? What are the conversations that you're having with, are these composite applications? We hear a lot about it in our industry. I'll let you talk about that. What are the big opportunities or the big applications that you're seeing right now for graphene?
Sure. Well, I'll start, and Kevin, who has to actually do the work, can come in and bail me out when I get it all wrong. This sounds a little strange, but our challenge is really focus and not breadth, right? Because we truly believe that there are thousands of applications for LTDF graphene. If you want to make something stronger, more electrically conductive, more thermally conductive, so on and so forth. So really, it's a question of, where do we have the highest value applications right now? One of those areas is drones, particularly for the federal government. We're going to be buying hundreds of thousands of Class 2 drones. These are the one-way, 1,000-kilometer range drones. What graphene can do is really transform those drones to help them fly further, loiter longer, carry heavier payloads, be more impervious to electromagnetic interference, and also to be more resilient against EMI and other attacks. So that's one of the things we're working on right now, is drones and how to incorporate our material into that. But also there's critical minerals. Everyone knows that we face a critical minerals shortage. There's no secret there. It turns out, from research studies done by maybe hundreds of institutions around the world, Kevin can talk to this in just a moment, we find that LTDF graphene naturally can replace some critical minerals. It can reduce the need for others, and it can amplify many of them in materials. So if we face a scandium shortage right now to make aerospace grade or military grade aluminum, by adding graphene to a unit of scandium, we can produce just for the sake of illustration, maybe 3 or 4x the productivity of
Wow.
that 1 unit of scandium. And so that's another area where we're looking at very hard. And then another and third area, and I'll stop after this, is trying to create or work with those who are trying to create rare earth free magnets. Everything runs with magnets these days.
Absolutely.
And particularly, the more high value, the more demanding, the more magnets are important. Well, the magnetic materials, the rare earths, tend to come from challenged country sources, particularly China, but not just China. There are others as well. Other technologies are being developed, like iron nitride, to create permanent magnets, but they face challenges. And so LTDF graphene can be used to overcome the challenges to create iron nitride magnets that are as good as or better than rare earth magnets. Kevin, do you want to talk a little bit about some of the applications that you've been working on in particular?
Yeah, great overview, Brad. And as Jonathan mentioned, there is a lot of opportunity. And so some of it is deciding, where do we want to do depth and really focus our finite attention and capabilities. And so we acknowledge, and one thing that I always have to tell people is graphene is a family of materials. Like we've talked about, there's all kinds of different grades of graphene, and some are good enough for applications. Like take Ford, for example. They commercialized using graphite nanoplatelets, and it worked for what they needed. It's cheaper. A lot of graphene companies might be targeting cement or asphalt, things. Sometimes, good enough is good enough for those. But when you think about really high demanding applications, really high mechanical strength, and more importantly, conductivity. And so that's where our large sheets really become even more important and differentiated versus small sheets, right? So if you think of what do we need to get conductivity in a polymer, right? We need basically a continuous path through it, right? So if I'm using large sheets versus tiny sheets, think of how many more junctions are needed between sheets for the small sheet example, right? And each one of those junctions where the electricity has to hop from a tiny sheet to another tiny sheet to another tiny sheet, you're paying a penalty in resistance, right? So typically you have to overcome that with much higher loadings like we've talked about, or it's just never going to be as high a conductivity as something where you're using a large sheet. So that's where we're seeing some really encouraging data in both thermal conductivity and electrical conductivity. And that goes back to some of the EMI shielding examples that Brad talked about. And so we're really able to see great improvements there, as well as corrosion resistance, for example. If you want something to be resistant to corrosion, there's a lot of coatings for that. But if you're putting in tiny sheets instead of large and thin sheets, then you're going to need more of them, or you just have to have all of them overlapping. So you're using more again. So, sometimes in this family of materials, graphene, there's all types of different applications and uses, but those are the ones that we're targeting really demand the largeness of the flakes, as well as the thinness for that conductivity and the lack of defects. Again, really helps with conductivity. Because graphene oxide, which a lot of people use, is not conductive at all. It's okay if you're using it in asphalt or cement, which doesn't need to be conductive. But when you want, materials with high thermal conductivity, for example, looking at, data center heat dissipation, or on a drone heat dissipation.
I was just thinking about data centers when you were talking, the amount of heat that's, like you said, dissipated in that. And then we've had guests on talking about orbital data centers, which is kind of the next step, as these things take up space, and, there's so much pushback from a local standpoint and getting these, from local municipalities. Some people are not happy with them. So, now we're looking at low orbit data centers, right? So we've had some guests on recently talking about that, other low orbit applications as well.
Well, think about this, Jonathan. Think about this. 40% of the electricity usage in a typical large data center is to cool the data center, right?
Yes. Yeah.
Why do we need cooling? Because we have the chips, and we connect the chips with a metal.
Right.
And regardless of which metal you use, copper, silver, gold, platinum, it has resistance. And
Hmm.
it's resistance in the metal that causes that heat to generate for the most part, not exclusively, but for the most part. Now, what if you took out the metal and you put in LTDF graphene, which is an incredibly, exceptionally conductive material? What would you do? You would immediately reduce the heat that's generated because you're using a material that doesn't have that degree of resistance.
Right.
So instead of thinking about putting data centers in space, why don't we take the little step of taking electronics, high
Hmm.
power electronics, and instead of using copper, use LTDF graphene in some epoxy or other material to
Right.
connect those chips. That's
Yep.
a pretty easy solution. Now, we haven't done, as far as I know, could be wrong, any work on that yet. But
Hmm.
I think the evidence is crystal clear that that will work.
Yeah.
Yeah, and let me talk a little bit more about that. There's so much
Hmm.
data out in the literature space and startup space about graphene, and this really led to a hype bubble that kind of burst
Right.
maybe 5, 6, 8 years ago, right? Where one of my favorite phrases is graphene can do everything except leave the lab. And so you hear that from
Exactly.
time to time. That's because a lot of the data that was being generated at the academic level or at some of the startup company levels, they were using a similar material to what we make, LTDF graphene. The problem was it's being made in these non-scalable ways. So the data that was being produced at, let's say, MIT, right? They released a study about it being superconducting or whatever. And this was maybe 10 years ago. They released this study and everyone goes crazy and the news organizations pick it up. The graphene they used was extremely high quality that the grad student made in the lab using a
Hmm.
very special technique that isn't scalable. So then the news organization picks it up and everyone says, okay, why aren't we using graphene? It's because the material that the study was made on isn't
Yeah.
industrially available, right? So there was that
Sure.
disconnect in supply and scale, as we've talked about. And one of
Yep.
my favorite papers came out, I think it was 2018, where they did an independent survey of maybe it was 60 different graphene companies. It was
Hmm.
published in Advanced Materials, and they said that 90% of these companies that claim to sell graphene aren't making graphene. And so that was a really big wake-up call for the industry. We need more standardization, things like
Right.
that. And so I think now we're really approaching a more controlled market, and now we have access to some of these really high quality graphenes that used to kind of be trapped in the lab or trapped at the lab
Hmm.
scale. And so
Yeah.
everyone knew that it was an incredible material and it had all these capabilities, but then you tried to use it in an industrial scale application, and you just didn't have the feedstock available that they
Yeah.
were using in the industry or in the academic lab. So that was one of the big disconnects that you kind of learn about talking with people, and everyone's heard of the hype of graphene, but that's the reason why it hasn't translated yet, because what everyone was using in the academic lab to get the amazing results wasn't available to buy because no one had figured
Yeah.
out how to make it scale.
Yeah.
And just if I could just add one thing to that, because Kevin, that is so important, the point you just made. So that led then to people trying to find ways to make quote unquote graphene. And that's why we have so many different types of material that are called graphene, because people saw that need and tried to enter the marketplace with technologies that were available rather than looking at what the market needed and trying to figure
Right.
out how to create that material. And I think that's what makes Avadain's journey different.
Yeah. What do they call that? The valley of death, going from the lab to
Scaling
scale.
from the milligram to the kilogram to the ton scale. Absolutely. Yeah. And I don't think anyone, back in 2016, 2018, I don't think there were nefarious people just trying to dupe
No.
people.
Yeah.
They were
No.
just
Yeah.
limited by the
Sure.
physical means of production. And that's another one of my favorite examples is aluminum. So aluminum used to be incredibly expensive, more valuable than silver and gold, actually. Everyone knew it had these, it was corrosion resistant, all these great properties, but no one could make it until
Mhm.
two scientists discovered electrolysis. And now we have aluminum foil, aluminum doorknobs,
Absolutely.
aluminum planes.
Right.
So sometimes you just have to discover a new method of making a material for it to
Yeah.
really hit that hockey stick and start seeing use in industry. So
Yeah. Yeah. I think it's like that with a lot of technology, right? I mean, there's a huge hype when in research when R&D comes along, and then it's the hype machine goes, it gets ramped up, and typically it's not right away. So I want to ask about your model, because it sounds to me, and you can correct me if I'm wrong, you guys are using more of a licensing model instead of doing the manufacturing yourself. If you would talk about that, because I think you've worked with Harcross. I'm familiar with Harcross Chemicals, and as I think they're one of the first manufacturing licensees, if I'm not mistaken. Maybe you can share a little more about that model.
Sure. Yeah. We're focusing on what we're good at, and we're trying to partner with people for things that they're good at. Right.
Yeah. Right.
And so this is now 10 years of development and deployment in getting the LTDF graphene right. And so that's great. We're extremely happy.
Mm-hmm.
We've got a lot of applications development in the line that we're working on. All of, the demand is there. There's no question about that. That's all good. We're not manufacturers, and that is a separate challenge altogether. So we partnered initially with Harcross Chemicals, which is an employee-owned company, 110 years old or something like that. Great group of people, easy to work with. The cultures align really well. And they're really good at manufacturing specialty chemicals and advanced materials. And it turns out that they have technology that can make the application of our graphene more plug and play for manufacturers. And so they've become the first licensee. We're building a plant for them right now. Their goal is to have 10 full-scale manufacturing plants online in the near future. Call that 2030. I don't think there's a specific time commitment there, but that's their goal. We are also talking to other chemical companies and advanced material companies about using it in different market verticals. So, our challenge really at this point is how to scale to meet the demand. That's really the issue. And one of the more interesting things about graphene is that it doesn't lend itself to centralized production. And the reason is that when you store it and then transport it, it tends to aggregate, to agglomerate.
Sure.
And so one of the reasons we were able to get the federal grant back in 2022 was we wanted to create a widely distributed production network using licensees.
Gotcha.
And the government saw that as really a distinguishing factor that was in the national interest, so that we will have different companies in different cities producing graphene that is available for their local manufacturing, so we can avoid the transport piece. Because this is more metaphorical than it is scientific. But if you take a 3 kilogram piece of graphite, right, a lump of graphite, and put it in a 40-foot container, you can barely see it, right? It looks like a pebble.
Right.
Now, if you put it through our process, it's going to fill that container completely, and it's still going to weigh 3 kilograms.
Right.
So the challenges of using graphene also are physical, the handling of the material. So the closer the material can be manufactured near the end user, the industrial end user, the easier it's going to be for industry to cope with that.
Sure. So the challenge, or I should say the opportunity, is with, you license this technology to companies that are close to probably end user type manufacturers that would.
Right, exactly. And when you have an established chemical company like Harcross, they have established clients, and they have plants near their established clients.
Okay.
And so we will have smaller production plants within existing facilities at Harcross, and in some cases, even end users, to produce it for those particular clients that they have. They come with their own customers.
Sure. Oh, yeah. I think that's super smart from my standpoint.
And Harcross has been a really perfect partner as well when we talked about aggregation and how do you disperse it well. They have a massive expertise in surfactants and master batching and pre-pregging and things like that. So they have a ton of experience that has been just wonderful there. And then I also just wanted to touch on, if we're able to have those, a distributed network, we're able to let end users focus on their specific application, right? And so another big flaw in early graphene marketplace, I feel like, was they just kind of shipped them the powder. They said, here's the powder, you figure out the rest. And now the industry, as well as Avadain, is really focusing more on admixtures. What can we do to make it really easy for you, the end user, to use? Whether that's in thermosets, cement. Some graphene companies are really going all in on admixtures for cement and asphalt, and kind of taking out some of that variability, making shipping easier. It's kind of more of a formulation plan now. So, yeah.
No, I think that's a great model. So for our listen, or for our industry, partners, I'm familiar with Harcross, but I don't think they're as familiar in the composites industry. But for companies in our industry, you would be interested in working with or licensing this technology to probably more like, resin manufacturers or companies like that are already have, they already have a built-in list of customers that they're working with.
Exactly. Yeah. We're not trying to displace anyone.
Right.
One of the things about the licensing model, right, is that I have the choice of making a company like, let's just say DuPont, right? For just picking a familiar name out of the hat.
Yeah.
Well, they could be my competitor.
Sure.
That would be bad. Or they could be my partner by being a licensee.
Right.
That would be good. And so we want to work with the chemical companies and advanced materials manufacturers that composite companies already work with, right? You have a relationship with them.
Yeah.
We can set up for you, and you can manufacture the graphene that goes into your customers' products to make them better, right?
Absolutely.
And then everybody wins. Everybody makes a little bit of money in the value chain.
Yeah. Yeah, absolutely. You work with within the parameters and the companies that have those established relationships and that those networks. So I think that is a great way to go. Guys, I wish we had more time. Time flies. I've got the website streaming at the bottom. People can learn more. Probably the best way is just to go to avadaingraphene.com. We'll have the website on our show page as well once we post this episode. So, and they can learn more. It's a great website full of information. People can check it out. Aside from Kevin, Brad, or who else? How big's the rest of your team right now?
Oh, we're small. We've only got 6 or 7 people at any given time. We are hiring though.
That's all you need though for what you guys are.
Well,
that's great. You're hiring. Okay.
Well, everybody works real hard. We probably could use a few more people.
Yeah.
And we partner with some great labs too, whether it's Mississippi Polymer Institute, Southwest Research Institute. There's more out there that I could name, but those are 2 of my favorites to work with. So.
Yeah, absolutely. That's a great point, because academia, that plays a huge role, and I'm sure that you get a lot of support from a lot of these universities and their lab, their research departments too. So that's awesome, man. Such a great episode. Thank you both for coming on. Very interesting. Look forward to getting this out, and if you guys are okay, next week we'll be publishing this episode or putting it out there. We'll certainly share it on LinkedIn and all of our social platforms, and be sure to tag you guys on this episode.
Great. Well, thank you so much, Jonathan. It was great talking to you. We really enjoyed it.
You as well.
Thanks for setting this up, Jonathan.
Yeah, thanks so much. Have a great weekend. Hold tight. I'm going to wrap up, and then I want to talk to you guys real quick on the back end.